Hello learners, welcome to session 6 of Unit 3 in this course. In this session 6, we are looking at fundamental theorem of arithmetic. I am Unkaila Dasmani, your course instructor. In this session, we will state and use the fundamental theorem of arithmetic. By the end of this session, you should be able to prove the fundamental theorem of arithmetic, that is FTA. Apply the FTA in other proofs. We should also be able to relate the FTA to GCD of sets of numbers. Okay, so let's look at small history about this. Every integer can be expressed as a product of primes, and this expression is unique up to the order of the primes in the product. This important insight into the multiplicative structure of the integers has become known as the fundamental theorem of arithmetic. The relationship between primes and non-primes is expressed by the prime power factorization of integer, and this is described in the fundamental theorem of arithmetic. In the book Xi of Elements, Euclid gives a proof of the infinite of primes, one of the most elegant proofs in all of mathematics. So let's see the way forward. So let's see theorem, fundamental theorem of arithmetic. The fundamental theorem of arithmetic is very important. So let's state every integer greater than 1 is either a prime or product of primes. Thus every integer m can be written as m equals to p1 exponent n1 dot p2 exponent n1 dot p3 up to pk exponent nk, where p1, p2 to pk are integers, are prime numbers raised to the power integer powers n1, n2, n3. So the n1 to nk are the integer powers and p1 to pk are the prime number. So every integer greater than 1 can actually be expressed as this. You mentioned them. When I have, let's say 10 will be equals to 2 multiplied by 5, and it's p1, p2, power 1, power 2, power 1. When I have 4, 2, power 2 in that order. So any integer greater than 1 can actually be written as that. So furthermore, for a given integer such as product of powers of primes is unique up to the order of the primes. To refer to such products as the prime power factorization of the integer m. So here we made mention of two main claims, and that is existence results and the uniqueness result, which are very important. So similar to the division algorithm, the fundamental theorem of arithmetic makes two distinct claims about every integer than 1. First, the fundamental theorem of arithmetic is an existence result, guaranteeing that every integer greater than 1 can be expressed as a product of primes raised to the powers. That's the first one, the existence. And secondly, the fundamental theorem of arithmetic is a uniqueness result, and this is ensuring that every integer has exactly one such prime factorization up to the order. So we will see an integer's unique prime factors and play a pivotal role in understanding and proving many insights into the properties of integers. Great. So the next, let's see the proof of prime power factorization. As we stated earlier, we will prove this existing part first. This proof is very simple, and I think going all these two, you can go through this, is also in your course material. Assuming to the contrary that there exists an integer greater than 1 that does not admit prime factorization, then the set of positive integers greater than 1 that do not admit prime factorization is non-empty, and hence by a well-ordering principle there must be at least positive integer greater than 1 called A. And I think you go through and read, and don't forget about your definition of prime numbers. So continuation of the proof. If B equals P1 up to Pk, C equals Q1 up to QL are prime factorizations, then what can we say? When A, which is BC, is now the product, you are multiplying them together. So when you take the product from here to here, dot from here to here, and this is a prime factorization of A, and that contracts A. So hence no such integer A can exist. So we therefore prove on the existence theory or existence part. So we prove for the uniqueness of prime factorization. The same thing, you go through your course material, you read through. So suppose that A is equals to, as we've already mentioned, and this is same as Q1, M1, Q2, M1, the equivalent, where Pi is 1 to S, distinct primes, Qj are distinct primes, Ni and Mj are all positive integers. So by distinct prime, we mean that B equals P1, P2. Ps are all different from one another, so you multiply them as I did, then 2 times 5. Since P1 divides A, and let's see the next slide. Since P1 divides A and A equals to this man, and that is A, then we can say that P1 must divide this. Now, since P1 divides the product of this, it might divide one of the factors of this product. That is, it might divide one of the Qj, since the only positive divisor of Q are 1 and Q1. We find that P of 1 equals to Q of 1. So let's continue on the proof. So going through, you can see that we've already made mention of that P1 equals to PQ. We consider this integer and you go through, and by the assumption that A naught is greater than 1, we get A prime equals to this man. Okay, so by the uniqueness of prime factorization of A prime, we find that the statements are all true, and after relabeling the primes if necessary, Pi equals to Qi, and similarly Ni must be equals to Ni for S equals to T, and that proof for the fundamental theorem of arithmetic. Okay, so go through your proof in your course material, they are all there. So example 22, find the prime power factorization of each integer. Oh, I think this one is just a basic, you can do it. That is basic one. Basic one you've already taught your students. So 30, we want to find prime power factorization, and that will be 2 first prime number, 15, 2 going to 15, then the next prime number that can go to 15 is 3, and 3 go to that 5. So this is so simple. Let me do the maybe last one for you. The 12. 12 will be equals to maybe that is 2 by 2 by 3. So I can say that 2 squared times 3. In that order. So you do the rest. This is so simple and it's elementary. Sequence of prime numbers. What is the set of 3 sequence of prime numbers? So we show 3, 5, 3, 5, 7, the only 3 sequence of prime numbers, and that is true. So suppose P plus 2, P plus 4 is a 3 sequence of prime numbers. From 3 we add 2 get 5, add 4 get 7. We are assuming that these are the only 3 sequence. Then we can write the sequence to be 3i, or 3i plus 1, or 3i plus 2. In short, any sequence of integers n plus 2, n plus 4. Exactly one of these is divisible by 3, and that's describe the sequence of prime numbers. Now prime in the form PQ BQ plus R, remember the remainder theorem, where B is a positive. So suppose that A and B are integers with B not equal to 0, then there exists unique integers Q and R such that the R is the interval with B positive. So this condition hold A equals BQ plus R. So this is something we have done it already, so we leave this one for you to go ahead. So example 25, find the integers x and y such that 512x plus 320y equals 64. We said we solved this one in session 5. We talk about this example. Let's look at the solution now. So the first thing to do is that we find the GCD. We are using the division algorithm approach. So to find the GCD, we start with the 512 equals to 320. Will go into that 1, and then remember how many? So remember 192, and also 320 will be equals to 192. Will go at the how many times 1? Remember how many? Remember 128. Similarly, 192 will be equals to 128 will go into 8. How many times 1? Remember 64. And then you can also write 64 or the 128 and equals 64, and to go into it, how many times 2? Right, 0. So in that instance, we can say that the 64 is our GCD. So GCD of 512320 equals to 64. Okay, and I think we've already talked about this. So to find the other one, in order to find x and y, let's call this equation star, where we have 64 190 equals 128 times 1 plus 64 equation star. If that is the case, then what can we do? Or we call them equation 1, 2, and 3. Let's call them in that order. So when I call them, you know the equation I'm talking about. So I'm calling this equation 1, equation 2, and then equation 3. Okay, so from equation 3, what can you see? You can see that 64 is equal to 64 because 192 minus 128 times 1, and I think you agree with me. And then from equation 2 rather, from equation 2 we can also have 128 times 1 same as 128 equals 320 minus 192. So you can see that this equals to 192 minus 192 minus, then I bring my big bracket, 320 minus 192, don't forget all times 1, and that is from equation 2. We have something like this. Sorry for that. Okay, this one is bracket. So in that instance, we move on to from equation 1, or this one. Let's simplify this one further before you go to equation 1. Let's go to the next page to do that. So we can say that this is equal to, by simplifying that, we had 192 times 2, because we're having 192, another 192. So 192 minus 192, they are all 1 get 192, and then minus 320 times 1, the same as 320. Okay, so then move on to equation 1. Equation 1, what can we say about equation 1? Equation 1. But because it's minus 320, let's try to do some small working here. So 192 times 2, so here we can say plus 320 minus 1. We want to get the 320 in equation 1. And then the 192. So now let's go to equation 1. Equation 1. So 192 will be what? 512 minus 320 times 1. I think we agree to that. So this will be equal to the 64. 364 equals to 64 equals to, so here 64 equal to. So this will be equal to 3. That's 192. We are going to substitute from equation 1, so you can get 512 minus 320. 512 minus 320, and that is, you are multiplying by 2, and that is true. 2 is here. And we also have plus our 320 minus 1. Okay. So we can simplify this further. So if you simplify or expand the bracket, we get 512 times 2 plus 320 times minus 3, because there will be minus 2 here, another minus 1 here, so minus 3. So what can we see? Therefore, we can write 64 is now equal to 512 times 2 plus 320 times minus 3, and that will be equal to 512x plus 320y. Therefore, x equals 2 and then y equals minus 3. Okay, so that's solved this question. So remember, I say all here, you can write 64. Okay, and that is perfect solution to this question.